Hi friends, let us in this video discuss about the and distinguish between the different types of basic stresses to which the mechanical components are normally subjected to. So first of all, let us see tensile stress. So what is tensile stress? So I have shown here a rod which is subjected to an axial load which is having the cross sectional area B into T in the side view, which we can see, and its length is L. So it is subjected to tensile stress, and tensile stress sigma T is equal to axial load which is normal to the cross section by the area taking the load, normal area which is taking the load. So load by area, normal area. So if we are mentioning a load in or force in newtons and B and T, that means cross sectional dimensions in mm and mm respectively, I will get sigma T tensile stress is equal to Newton by meter square or Newton per meter square. But we know that 1 Newton per meter square is equal to megapascals. Now let us go to the second stress. So same thing, similar block I have taken, similar bar I have taken, which is having length L and cross sectional dimensions B and T, that is width B and thickness T, and it is subjected to compressive force. So definitely compressive stress sigma C is equal to load by compressive load by area which is taking the load, normal load which is taking the normal area which is taking the load, that is P by B into T. Again, once again, if P is in newtons and B and T are in mm, I will get area in mm square, and sigma C compressive stress in Newton per mm square or megapascal. 1 Newton per mm square, we know that it is definitely equal to 1 megapascal, right? So in the third figure I have shown you. So I have shown you here, this is tangential shear stress. For example, I have same block I have taken or rod I have taken, which is having the rectangular cross section area B into T, that means B width in mm and thickness again T is in mm, but it is subjected to tangential force Fs, shear force or shear force. So I can see that the top area, which is nothing but your L into B, is subjected to the shear force. So definitely shear stress is equal to shear force or tangential force by area resisting the force, tangential force or shear force, that is shear area. I will call it as shear area. So shear force by shear area, we can see this particular area in the top view only, that is L into B. So for the dimensions L into B into T, I can see the top area which is subjected to the shear force, which is nothing but L into B. If Fs is in newtons and L and B are in mm, I will get directly the shear stress tau in Newton per mm square or megapascals. Now let us go to the next one more important stress, that is your bearing stress. So bearing stress, I have shown a shaft and a bearing which is supporting the load W, and let us say D is the diameter of the shaft and L is the let us say length of the bearing. So definitely for calculating the bearing pressure or bearing stress, I have to take the projected area of the surface area which is in contact, that is bearing area which is in contact. We know that surface area which is in contact with the shaft, bearing area is equal to pi dl, but I am not going to take that area. What is the area which I am going to take? I am going to take the projected area of the cylinder. So that means the projected area of the contact, so which is nothing but pi dl. So if you project a cylinder which is having a diameter d and length L, which is having the surface area, but in the top view I can see that it is only d into L, that is the projected area of the cylinder is equal to d into L, where d is the diameter and L is the length of the cylinder. Similarly here, the projected area, that is the area of the contact of the bearing with the shaft, is the projected area is equal to not pi dl but dl. So I have to take the projected area for calculating the bearing pressure or bearing stress. Once again, if the radial load is equal to W and L and D, that means length of the bearing and diameter of the shaft are in mm and mm respectively, I am going to get the bearing pressure or bearing stress equal to Newton by mm square or Newton per mm square, that is your megapascals. Okay, once again let us go to the next one, that is your crushing stress. Last one in the basic types of stresses is the crushing stress. So you know that for every component or any material, so or three-dimensional article or bar, it will be having 3 dimensions. One is the L, length, and B is the width, and T is the thickness. So if I am applying a axial load, let us say P, I have applied. So definitely under the action of the load, either the cross sectional area T into B may break, or if it is weak in the frontal area L into B is going to break or is subjected to failure. So I have to take the frontal area to calculate the crushing stress. So the nature of the crushing stress is always equal to that of the tensile stress. So the nature of the crushing stress and tensile stress both are same, and to calculate the crushing stress I have to take the frontal area. So what is the frontal area here? L into B. So once again I am going to get the sigma crushing or CR, sigma CR or whatever it is. I have here denoted by sigma c. Sigma crushing is equal to axial load by the crushing area. Crushing area is the frontal area, but frontal area is equal to L into T. I know that it is L into T. So if once again, if P is in newtons and L and T are in your what you call mm, so L mm and T mm, I am going to get Newton per mm square. That is again once again I am going to get the sigma crushing stress, sigma c crushing stress in Newton per mm square. That is your megapascals. Okay, guys. So today what we have seen? We have seen the basic differences between the, we have distinguished actually between the tensile stress, compressive stress, tangential shear stress and bearing stress, and also crushing stress. There are some more stresses like bending stress, torsional shear stress and thermal stress, and also impact stress. So all these stresses we are going to discuss in the next video. Once again, let us meet in a good video shortly. All the best.